Hi there, my name's Alicia Story, and you might recognise me from the how-to sessions yesterday. And we have a really exciting one lined up for you now on biodesign. So, biodesign is an exciting and emerging field of design, all about learning and working with nature in your designs. Biomimicry is where we copy nature's patterns, and biophilia is where we try to replicate nature's forms in designs. However, these terms really refer back to looking at biology in terms of, and then using this to design solutions. So, Veronika Kapsali has been working to create a course called Biodesign, which helps people learn from biology and apply it to their designs. Veronika is Professor of Materials Technology and Design at the London College of Fashion, UAL, where she holds the position of a AHRC Leadership Fellow in Bio-Informed Design. She's going to share some key elements through the video that we're going to just put up now, where you can find out all about biodesign, and then we'll have a very short Q&A at the end because the video itself is a little bit longer than the session. So yes, I shall see you in the Q&A soon.
Welcome everyone. My name is Veronika Kapsali and I'm the Principal Investigator of the Bio-Inspired Design Project. Today I'm excited to share insights on how to incorporate biological ideas into your design practice and how this novel approach can lead to outcomes that are resource efficient. We'll begin with a short animation to introduce the Bio-Inspired Design Framework and discuss our recent maker collaboration supported by the Design Council. Later, we'll delve into inspiring case studies highlighting how BID principles can transform design practice. Finally, we'll be providing information about our up-and-coming online public BID course. Before we proceed, allow me to introduce the BID team. I am Veronika Kapsali, a Professor of Material Technology and Design at the University of the Arts, London. Dr. Catherine Annika Hall, a design and sustainability researcher who specialises in mechanical textile recycling. And Steph Rolph.
Hi everyone, my name is Steph, a design researcher with expertise in sustainable textile design in both academic and industrial sectors. So, let's begin with a short animation introducing the project.
In a world striving to achieve net zero and reduce the negative impacts of our design practices on the planet, Bio-Inspired Design, or BID, is a research initiative that aims to enhance the sustainable design skills of creative practitioners by tapping into the wealth of knowledge found in biology and material science and bridging these with the world of design. Traditionally, our efforts to achieve net zero have centered around swapping materials for more sustainable alternatives, a crucial step indeed. However, we may have been overlooking an essential aspect: our own skills as designers. Nature, with its incredible array of plants and animals, has mastered the art of survival and growth using a limited range of substances. Unlike us, who have developed countless plastics and alloys that don't exist in nature. But what if we could learn from plants and animals? Zoologist Professor Julian Vincent and his team of engineers and material scientists have shown that plants and animals achieve specific behaviors and properties not just through substances, but through structure. This revelation has profound implications for improving the efficiency, longevity, and recovery of resources used in product creation. Thus, the Bio-Inspired Design Framework was born, based on a comprehensive review of scholarly studies led by material scientist Stephen Nalloway, exploring the relationship between structure and the extraordinary mechanical properties observed in biological materials. Stephen developed a visual code transcending cultural and language barriers to define the reoccurring structural elements responsible for the remarkable properties of biological materials. This breakthrough made it easier for material scientists to share knowledge and allowed designers to access previously exclusive insights. Building on this foundation, our team transformed Stephen's model into a practical design framework, complete with guides, tools, and examples. This empowered designers to incorporate ideas from biological structures into their own practice. Through an interactive online course and collaboration with over 200 designers worldwide, the BID framework evolved. This initiative helped designer makers reimagine their existing skills through a bio-informed lens, resulting in innovative design proposals. We chose the most promising proposals to become a portfolio of examples showcasing the BID framework. Its aim? To inspire and guide other creative practitioners in their sustainable design journey. The initial analysis of the outcomes from the maker collaborations have revealed some really exciting findings about the BID framework. We've learned that it can enhance sustainable design skills by promoting strategies such as monomaterial and disassembly approaches for resource recovery. Additionally, it can consolidate manufacturing processes, reducing material inputs and enhancing energy efficiency. Moreover, the framework introduces innovative concepts of adaptability and modularity, contributing to the longevity of designs. These discoveries hold great promise for a more sustainable and eco-friendly future. The biodesign framework serves as a bridge between creative and scientific disciplines, unlocking a wealth of untapped knowledge for a net zero future. It empowers designers to embrace nature's wisdom and become catalysts for a more sustainable world. Having worked in bio-inspired design for over 20 years, I've often encountered a challenge: the scarcity of practical examples of bio-inspired design within everyday products. While there's a lot of work happening in biomaterials, where designers collaborate with microbiologists, there's not much evidence of how to learn from the way materials and systems are structured in biology. Before we embarked on the journey resulting in the Maker Collaboration Initiative, we conducted a survey of over 300 designers across numerous disciplines and from all over the world to understand the role of biology as a source of inspiration in their design practice. From this, we learnt that the vast majority of you regularly draw on biology for inspiration. Because you believe that somehow this will address your concerns pertaining to the environmental impacts of your practice. However, when it comes to implementing ideas, you don't get beyond aesthetics, which is super important in enabling good design, but unlikely to contribute to the sustainability agenda. You told us the reason preventing you from deeper engagement with ideas from biology is lack of access to knowledge and examples of design practice. So we spent the last few years developing the bio-inspired design framework and collaborated with designer makers to demonstrate how it can overcome barriers such as access to knowledge and promote design for resource efficiency, longevity, and recovery.
To help us test the framework and develop tangible examples for other designers, we launched the BID Maker Collaboration, aiming to identify innovative designers and makers who could apply the BID framework across diverse design disciplines. We packaged the framework into a pilot online course. This interactive course introduced the 9 BID structures and the 3 sustainability pillars. We had over 200 participants from across the globe. Upon completion, those interested in our maker collaboration submitted design proposals.
From an impressive pool of over 60 design proposals, we partnered with the Design Council to select the final group of makers that represent disciplines spanning from furniture, fashion, industrial, and packaging design. In the upcoming slides, we will explore some of their innovative approaches to the BID framework. Our first case study focuses on Matter.
Matter is a dynamic creative studio composed of 14 designers and makers from multiple disciplines. The studio finds its inspiration in the transformative power of design for shaping a brighter future. They specialise in developing new products and immersive experiences spanning various market sectors. Their expertise spans industrial design, packaging design, visual representation and prototyping, catering to a diverse clientele that includes SMEs, startups, not-for-profits and multinational corporations. With us, Matter embarked on a journey to explore how their extensive proficiency in industrial design could synergize with the bio-inspired design framework. Specifically, they sought to understand how principles of resource efficiency, longevity and recovery could be seamlessly integrated into their innovative design practices.
Matter initially examined all 9 structures to explore their potential in wearable well-being devices. They focused their attention on the helix structure and delved into the possibilities it offered for managing acoustic properties. Through a series of iterations, they developed an adaptive helical system that allows the wearer to control the level of insulation provided by the device. The helical structure opened opportunities for resource-efficient solutions through monomaterial constructions and modular designs that facilitate disassembly at the end of the device's life cycle.
Currently, most earplugs available are disposable, often crafted from petrochemical materials or reliant on electricity for sound dampening. However, through the ongoing research and development efforts, Matter has successfully crafted an adjustable in-ear device that not only uses fewer materials, but is also more straightforward to repair. Employing a helical structure reminiscent of the sea auger shell, this earplug incorporates an efficient sound filter. The degree of sound attenuation can be fine-tuned by simply twisting the outer ring of the earplug to compress or expand the helical component within it.
The team at Matter has used this project as an opportunity to delve deeper into the advantages offered by bio-inspired design principles, particularly in enhancing the performance and sustainability of materials and products. The earplug's inherent simplicity, minimal parts, and use of a limited range of materials contribute to the resource efficiency and product robustness. These attributes ensure that it provides a straightforward solution for end-of-life recovery. Our next case study is a notable example of how the bio-inspired design framework can be applied to existing design practices and have a significant impact on material consumption and potential for material recovery.
Jo Wilton is a furniture designer and co-founder of independent manufacturing company And New. Since 2013, And New have been designing and manufacturing furniture in the UK with a focus on longevity, sustainability and community. With a background in sculpture, Jo's furniture pieces are influenced by her discipline and are material-led. Initially, Jo was drawn to the BID course, looking for a way to draw on her passions for horticulture and nature within her design practice. After completing the online course, she gravitated to the cellular structure. Natural repetition of geometric shapes aligned closely with her existing practice and design aesthetic. Considering the functionality of the cellular structure, their ability in nature to reduce material inputs whilst maintaining strength and volume, Jo was keen to see how this could be applied within her practice. Jo identified the JAA cube, a stool or side table within And New's existing product range, as a suitable candidate for a new BID iteration. This can be seen in the image on the left of the screen, a striking cuboid design made from sheets of recycled plastic.
Starting with small paper and foam board models, Jo was able to explore ways of creating the same striking volume that gives the JAA its unique aesthetic, whilst reducing the material. By substituting solid squares of recycled plastic for strips cut from large sheets, she reduced the volume of materials required. This substitution required new horizontal connections to hold the structure together, providing strength. This innovative approach provided the opportunity to remove the custom hardware used in the original design. The piece is held together with wooden rods, positioned in 3 directions to create a solid connection with no nuts, bolts or glue. Removing the adhesive allows for the replacement of individual elements if required, extending the longevity of the product. It's also easy to disassemble at the end of life, allowing the wood and plastic to be separated for material recovery. We've touched on some of the impacts the new cellular design has had on the product. The innovative design uses a repetitive construction model using identical elements in different directions, creating a cellular structure which adds strength and reduces material inputs. By applying the cellular structure from the BID framework, Jo has been able to deliver a stool which allows 75% less material than the existing equivalent pieces in her production collection, the reduction of components to only plastic sheet and wooden rods, removing metal nuts and bolts. This switch removes the need for the custom hardware, reducing the energy to manufacture. The strips of recycled plastic tile precisely into the sheet material, removing the offcuts. The piece has been designed to disassemble, enabling resource recovery. And finally, the cellular design creates added functionality. The piece has new shelves that can be used for storage.
Florencia Bordas is a seasoned fashion designer and pattern cutter with over 15 years of experience in the fashion industry. Her expertise lies in the crafting of exquisite bespoke clothing, including bridal and formal wear, as well as tailoring. Florencia's deep-rooted passion for artisanal craftsmanship served as a catalyst for her participation in the BID Maker collaboration. In a world where traditional sewing skills are becoming less prevalent, she embarked on a journey to explore how a novel garment system could democratize handmade fashion, making it more accessible to a broader audience.
Florencia initially enrolled in the online course to embark on a personal challenge and discover innovative solutions to the persistent challenges of fit, adaptability and durability in clothing, which she'd encountered throughout her extensive career in fashion design. As she progressed through the course, a concept had been brewing in her mind: modularity. Upon completing the course, Florencia was resolute in her decision to explore the sutra structure through hands-on experimentation. In the BID framework, sutra is a structure that represents the flexible and non-permanent value of different joins. This set Florencia on a creative journey in which she encountered challenges in working with interlocking fabrics, where texture emerged as a pivotal element, imparting essential durability and strength to her garments. Throughout her project, Florencia effectively addresses all three sustainability pillars, and we will delve deeper into her methodology to explore these aspects.
Modular clothing has been a subject of exploration in various forms within the fashion industry for many years. In this project, we collaborated with Florencia to transcend conventional approaches and design paradigms. Initially, her concept centered around a dress, but as the project evolved and her insights deepened, she gained the confidence to undertake the construction of a tailored jacket, a notoriously intricate item in terms of cutting and sewing. What set Florencia's research apart was her ability to tap into her extensive haptic knowledge of fabric and her innate understanding of how they drape and respond to the body. This allowed her to pinpoint issues within the interlocking modules. To address these, she used laser treatments to introduce texture that significantly enhanced both the drape and durability of the garments, particularly around the shoulders and hips.
These garments embody innovative features. They're not only repairable, but also highly adaptable. The interlocking pieces, comprising just 4 standardized shapes, can be readily replaced if they incur damage, eliminating the need for professional repair services. Moreover, the design incorporates small components that facilitate adjustment, such as letting out or taking in, altering lengths as needed. At the end of their life cycle, these mono-material pieces can be effortlessly separated and recycled. Furthermore, the jacket contributes to sustainability by reducing the reliance on traditional components such as interlining, stitching thread, and interlocking threads. Instead, the laser-cut surface of the tabs serves to provide the necessary strength and stiffness, thus diminishing the number of elements typically found in a conventional jacket.
Yinglun Mao is a multidisciplinary designer working at the intersection of art, design and technology. Being educated in industrial design and material research, his practice centers on an investigation of how production of physical objects, through hands-on experimentation, novel technologies and methodologies, can allow for ideation and experimentation.
Yinglun took part in the BID Maker collaboration to explore how the new knowledge he gained through the BID online course could be embodied in physical products, exploring the gradient and cellular structures. It provided the opportunity to move beyond a focus on material properties, i.e. choosing a specific material to add strength or stretch to a product, and instead consider how structure can be used to deliver equivalent properties. This is the core principle of the bio-inspired design framework, moving from material to structure to deliver performance within our products. Drawing on the gradient structure found in an ostrich's toe, Yinglun developed a concept for a monomaterial, shock-absorbent knee pad. Yinglun applied his knowledge of parametric design to recreate the 3 distinct areas of varying density observed in the ostrich toe. Transitioning from a dense outer section towards a more open cellular structure, the concept intends to absorb impact. The design also features a bumpy external texture, reducing the contact area with foreign objects and thus minimizing wear during use.
This is an example of how digital manufacturing can enable the implementation of complex structures such as those observed in biology, using them to create products for humans. Yinglun's idea encompasses the potential to combine body scanning for custom-printed knee pads tailored to individual bodies using additive manufacturing techniques that incorporate 3 different areas of density within a single piece, negating the need for additional adhesives or connectors. Just 20 years ago, a concept like this would have been considered science fiction. Emma Fox is an international award-winning designer, educator and facilitator currently engaged in training, research and commercial design projects. Her design practice ranges from ceramics to packaging, sustainable design strategy to furniture design. Her design research practice is transdisciplinary, experimental and material-driven, centred upon exploring circularity using radical reductive design thinking for industrial design through integrated product approaches, primarily working with waste textiles in temporal fashion contexts. It was curiosity that led Emma to take part in the BID Maker collaboration. Coming from an industrial design background, she wanted to view her research practice through a different disciplinary lens to see how she could push boundaries further. The BID concept of designing with structure rather than substance resonated with the temporal and transformative nature of her work. Gradient aligned closely to this approach, using varying densities to create different properties across a monomaterial, for example rigid and flexible areas. With a material like Kvadrat's really acoustic felt, gradient structures allow for different user experiences and functional expression of the material depending on the context and configuration of its density. Emma's ambitious proposal highlighted both the potential and challenges the BID framework can pose. Emma found that scaling the sample she had developed required the production of a custom heat press and ovens. The 3D corner samples demonstrate the potential for the combination of gradient and layer structures to develop a monomaterial cabinet that transforms from package to product. Proposing a radical alternative to cabinets that are typically made using rigid materials, for example solid timber, with fixings often made from metal. Emma's ambition of a monomaterial cabinet embodies the BID sustainability pillars. Through gradient, efficiency is achieved using a minimum amount of material with varying densities to develop rigid and flexible properties. Longevity is addressed through the gradient and layer structures. The material used in this project is both package and product. The material needs to last in a particular functional mode only as long as it is needed. Recovery is consequently addressed through the monomaterial approach, allowing ease of recovery in the right systems context. BID structures enabled Emma to push not only her product, but also her practice. The framework challenged her to solve physical and aesthetic challenges through density and configuration of materials, rather than resorting to more typical methods of problem solving. A great example of how the framework can both harness and challenge designers' existing approaches.
The collaborative journey with our team of designer makers didn't necessarily introduce new techniques or skills. Instead, it offered our makers a fresh perspective on their existing toolkits. This perspective deepened their comprehension of the intricate relationship between structure and function within their respective design disciplines. Consequently, it empowered these designers, granting them agency in addressing the efficiency, longevity and recovery of resource use associated with their industry's practices through creative design solutions. The Maker collaboration has played a pivotal role in providing these talented individuals with the support and expertise needed to nurture their concepts from initial ideation to functional prototypes. We're eagerly looking forward to further supporting these makers as they explore avenues for the commercialization of their innovative ideas.
It's not just the makers that we are hoping to support through the BID project. We are excited to be launching the public version of the online course later this year. As we mentioned at the start, all our makers, along with 200 other professional designers and enthusiasts, took part in the pilot. Their feedback, along with the case studies we have been able to build through the Maker collaboration, will be used to enhance the course. If you would like to sign up to alerts for the release of our online course, please scan the QR code on the screen.
This project has been made possible by the generous support of UKI Arts and Humanities Research Council,
as well as the Crafts Council, the Design Council, University of the Arts London, the Design and Technology Association, as well as the enthusiastic support of our dedicated makers.
What an incredible overview on biodesign, and the course looks incredible. I'm sure there's been some discussions on the chat on that, and that's also been provided the information at the end of the video. We're just at time now, so I'm going to have to close off, but I'm sure you can reach out directly potentially if there's specific questions as well. Thank you so much for that incredibly informative session. The case studies were fantastic as well to show it in practice, how it works, and also thinking about the collaboration from all the different designers initially to form the content. So thank you so much for that, Steph and Veronika. And yes, on to the next session. Thank you very much, and see you all soon.